That's how that works. Yeah. So. That again, a check. When it's after you've gotten an exam, that's when everyone's going, oh, what am I gonna do? Well, this is what you're gonna do, and it's just a different assessment. I would prefer, honestly, if all of ours, we didn't have so much work in kind of exams, which I don't think is fair to students, but I don't dictate that. That's dictated by the universities. So that's how I care about it, because in my opinion, you should have, like, if you can get up to a board and explain how to do a problem cold, why should you not get full credit for it? And you can do that also instead of a white paper. If you want to give yourself a video of you doing the problem and explaining each step, you'll also get full credit for it. All right. So, but that, as I said, that'll come in with. So that's what that's all about. Yeah.
I appreciate your means and methods. They're reasonable.
Well, I don't know about that, but they,
Yeah, and I
I
think
think they're better than what
we choose.
Pima gives, honestly.
Oh.
Yeah.
It's a workaround, so.
well, it is a workaround, but it actually, it's not coming from Pima, it's coming from the universities.
Oh, you're right.
Well, not like
Universities.
The universities are telling us 75% has to be proctored.
Yeah.
So my
I don't know if-
syllabus shows 75% proctored, which is the key.
Yeah, at the beginning of.
But then I allow you these other opportunities, and they do it at U of A, they curve,
Yeah, cause my.
they drop your lowest exam. I mean, they'll do things like that. They're just a little, but I don't think then that shows that you really understand.
Yeah, I used to work at that same.
You know.
Right.
Buffer everything.
Where I wanna see,
Yeah,
what do you understand?
Good.
Do you understand it? And, cause that to me is more important, because when you move into dynamics and solids
Yeah, yeah.
and all these other classes that you will
I
ultimately
mean, you're
take
more
as
like a
your
straight
mechanical
shot.
engineers.
Engineering management.
I go all the way.
Oh,
to
then you
half-
won't be taking those classes.
Still use this one though.
Yeah.
Yeah, you'll still have to take this one. You might have to take some of those, but what that's gonna do is that I wanna make sure this is your kindergarten, statics is kindergarten, you gotta have kindergarten down,
Oh, okay.
right?
Perfect. Yeah.
So, because you can't do count three, right, unless you don't count one.
Now that I think about it.
That's the way I look at
it.
Thank you. You're welcome. So you guys have a good one. See you Wednesday.
Absolutely, see that.
And yeah, hey,
You're
feel
up
free
for
to show up to class.
Thank you.
Holy.
All right, County people,
I didn't know the four was.
I was talking to static students about white papers.
That's a stingy cop.
Yeah, we left off. Was it sheriff?
Shitty version of that. And then he had to like.
You've been
take half
chilling
the
and
cost
calm
off,
still.
but
It was right on the morning.
We are going to start today with some group work.
Oh, shit, yeah.
So if you're virtual, take a picture. If you're in class, I will give it to you. All right? This is group work. This should look a lot like your homework, eh? Yeah. And it is a lot like your homework. So we're gonna do it as I said, group work. So you can work together and explain it to each other, and then we will, as with always with group work, I will then come in and show you how to do it in class. Okay? 3, 4. All right, Monday is group work, Wednesday is quizzes. So you work different parts of your brain on different days. We will do 2.1 today. We're gonna start energy balance expressions.
You graded it.
I graded it if you did it in person. Did you take it in person?
Yeah.
Okay, that's the wrong class. I mean, you can do statics. But that's the one that'll count points.
Doesn't hurt.
What? All right, are you taking statics? You don't have to.
You know what I might not.
Okay. All right, online people, Zoomers, give me a 7 in the chat once you have this ready to go. It's identical. I'm not that creative. All right, take a screenshot. I will get your thing. A thing is a very descriptive term. I will get your Dropbox set up. All right, go off to your rooms, unmute, talk to each other.
I don't think so.
Valerie, group work's right there. I know you don't get much of a break on Mondays.
That's just that's just like. Oh. Yeah, oh. Oh, this is right. Sabs. Oh. Oh, shit. Since this is. For L. Yeah. No, it's a change in type. Oh, so I had to kill next. Yeah, it's like the cheese. Like, you need to assume like is like this. I'm not sure. It has bottom pressure. Is like this. The air pressure like this. And that is. I mean, it's your sound. That's like the one. Yeah. So it's not all the time. But like if the water will push in. Up and it's not the pressure is pushing down. No. Not cancel out the pressure, but you know, kind of like 1.5 bar. Weight of the burn. So like if you know that, would you just because we know the pressure at the bottom, and then you start. It's just kind of density times. Yeah, there's a. What are the units for? This is a bar, so we can change bar to. Yeah.
Logan, Riley's not here.
Yeah, like that's the. Absolutely. Well, I guess.
It gives you the pressure at the it's like boxing, so it's like.
Someone check D2L, make sure these are in D2L. Logan,
Yeah.
Hector,
Because what we went
I
over.
don't see him. Daniel, Atreyu, Jeremy,
That's absolutely. I don't think we can. If we're giving the two ends of that. That would be absolute. Oh, no, I get, that's like absolute, right? Because yeah, sure. Like all the pressures on.
did Ben come back? Oh, right there.
So yeah.
Thomas, Demetrius,
But not the cast
and Valerie's up front. Gabriel,
Here's. I've had no professor say something.
Alicia,
So it's not.
No, I did put a free money diagram.
that's right, that'll smack you every time. Emiliano, anyone will tell you. Former static students of mine, what happens? What's the first thing you have to do? Yep. Lorenzo,
She's got a list.
free body diagram.
Wait.
Anthony and Martine, did he not come back in? Wasn't he here this morning for dynamics?
Yeah, he was.
Okay, Riley, Hector, oh, Valerie.
I'm just trying to see how she.
But no, on these, I'm not talking about this, I'm talking about statics.
Oh,
It's not about statics, free body diagram for statics. Because someone in the class mentioned how they got smacked upside the head in statics because they forgot their free body diagram. But they'll only forget it once and then they'll never forget it again. Never again. Why are you people not going to your breakout rooms? Go to your breakout rooms.
System as the.
Are you done with the problem? Tell me in the chat if you're done with the problem.
Like all the forces are acting on. I guess.
Oh, I can't see because this is in the way.
Gravity is down. Everything in them.
Okay, Luke, we're doing group work. Take a screenshot. Take a screenshot of the problem. And then I'll send you off to a breakout room, please.
That's just kg per kilograms. Keep it in bar. No, still.
Oh, you have been assigned. No, you're not assigned to one. ICU is not assigned.
Yeah.
But I'm gonna send you to room 3. There you go. You should get an invite.
This one's one, yeah. You know what? The atmospheric pressure. I think we're trying to find an atmospheric pressure.
Yeah, you added, that's exactly what.
Oh, I gotta find my standard pressures like shapes of what it's the same.
I know.
That's not always good.
Yeah, this is in the new.
Six. It's the closest. So.
Lorenzo? I guess I could watch. Valerie?
So gauge pressure is. I did always slow for pressure and then.
Logan? I
I
did have the dynamics quizzes. I just didn't think I did. Because I didn't look at the entire file. Jaden, he's not in here. Atreyu, I'm gonna hang on to yours. We need to get you back in the class.
Oh, yeah.
Right.
Right, yeah.
Christopher, Skylar, Anthony.
I think it's could be. Right. Just one of the guys doing water.
Yeah, but if you.
Yeah. So I just said. You get like 30,000.
Yeah, exactly, 30,000.
We're just trying to figure out.
Logan.
Oh, yeah.
Oh,
thanks.
Oh, really?
Yes.
No, that's the bottom pressure. So we've got pressure coming in from the water and from
So
the
it
air.
needs to be.
Just gonna combine it together.
Right, you have a fourth from the air and a fourth from the water. Yeah.
Right.
And I think it's 10 to the third, isn't it? Yeah, it should be 10 to the third. The density of water is 10 to the third.
Oh, shit. Can we just keep it like what it is right now?
Yeah, go ahead.
No, don't do that. I was gonna whack that number for my blood.
I got to.
Density of water is always 1,000 because it is how we,
That's. I don't know, so the problem is, I don't know.
Unless someone's supposed to.
20. This is,
Yeah, so basically, yeah.
this is 210. This is 210.
But I don't.
Pressured net.
Like he can fix it.
Here's a request.
Yeah, so.
Yeah.
So what is P? Like
It's
that?
Pressure.
So P lower is,
Yeah, it doesn't tell us
or like what is the?
It just says the pressure at the bottom.
I think slash. But this is my absolute.
Yeah. Yeah, that
This
is.
is the one that's like where you always start. What's your name?
Yeah, yeah, that makes sense. That's basically, it's like, basically like, so you have an air, so yeah, so it's just like air equals.
Because we got pressure on the bottom.
Supposed to be the bottom line.
Okay.
Which is the different
Vapors plus the one.
bottom.
Okay.
No,
I just gotta fix my. It looks.
Okay.
Okay, let's, we got a couple of folks that haven't popped back in yet. Once they pop back in, let's go over this.
I don't think you can put that in.
Density.
This right here. It's in G squared, so because of this.
2 meters.
Bars. I know I did, but I remember this in the whole place, like really, it was like a weird conversion they did. Like it
What
was
class are you taking?
weird.
Cal 2?
Intro to engineering design, oh my, or just engineering design. Manufacturing.
Oh,
I got that. Oh, okay, wait, so is this P, that's I.
so.
all right, everyone back now.
That's fine.
Those of you that are virtual, I will put this in the chat. This is the Dropbox you use. All right, okay, let's go over this problem and talk about what's happening. Now, one of the issues, I don't know why this is here and how to get, oh, I know, I'm frozen. All right, so we have a couple of issues which no one identified until a few minutes ago, but this is 10 to the third. So the class asked that we go ahead and do it as 103. All right. Yes, we're gonna do it as 103. You want to use it 10 to the third, Daniel? You can be the benevolent dictator for the class. What do you think?
I mean.
Dr. Minky, I think the screen is frozen.
I unfroze it inside the classroom. Here, let me stop sharing and reshare.
So you did it, it's just, I think I did it
Do you now see 10 to the third written on it?
Yeah.
Okay, and that's actually pretty standard, or not standard. Water we use for density, we use water as being our standard at, basically it's looking at 1,000 kilograms per meter cubed, and that's at 4 degrees Celsius, okay? So that when you take your fluids class, you're gonna use that a lot. Do you wanna do the density at 103 or 10 to the 3? I don't care. Do it as 103? All right, since I made that mistake. Now, we have pressure at the bottom of this, don't we?
Yes.
So would you agree pressure is coming in from the air and pressure from the water? Yes, no, maybe?
Yeah.
We agree on that. Okay, so. We are given the total pressure and we want to determine the pressure of the air. So this is what we're looking for. Here is our unknown. This is then 4.15 bar. Can we figure out what this is? Yes. Ben doesn't think so.
Oh, no, I do. I really do.
Okay,
I really do.
that's okay.
Two-body diagram.
No free body diagram. We're not in statics. We don't need a free body diagram. You need to remember this. This is your fluids class, all right? This is called Bernoulli's equation, rho G L. So pressure is going to increase the further down we go. I will bring them in. My husband took a series of pictures of me 2 weekends ago with a water bottle full of air. When it was on the surface, when we were at like 40 feet, and then when we were at like 60 feet. And what happens, the pressure of the water causes the water bottle to go and swoosh up. All right. So you care about this because, well, I don't know if you care. Yeah, you'll care. You'll care because you'll have to do pumping projects. Well, maybe not. Depends on what you're doing, but you might have to do pumping projects. All right. So the length is given to us as 30 meters, correct? All right, so let's go ahead and set this up. I have 4.15 bar, right? I'm looking for the pressure, the vapor pressure of the air, okay? Plus, I'm given density. We will calculate it with the wrong number, so I'm going to need calculators. 103. We are told the local gravity is 9.81. And we are at 30 meters. This is in kilograms per meter cubed. This is in meters per second, and this is in meters. So we're going to end up with a kilogram per meter, aren't we? So what do you come up with when you do this? And we end up with a kilogram per meter.
Second?
Second square.
Yeah, second square.
Oh, it is second squared. All right. The problem is this side is in bar, isn't it? By the way, what did you come up with when you put that in?
30,312.
Kilogram per meter second squared.
And it's minus. Minus, right?
Yeah, because it's coming over from the other side. All right, so this is not in bar, correct? We need to turn that into bar, don't we? So the best way I think to do it is 3312.9, right? A kilogram meter per second squared is also known as a what? So if I have a kilogram per meter second squared, that is then 1 Newton. So now we're in newtons. On your conversion sheet, can we move from newtons to bars? Yes. Because, oh, wait,
No, because that's, because a meter's on the bottom. We'd have to multiply times meter over meter.
okay, hang on.
It's the denominator, it should be kilogram meters over second squared.
All right, so let's back up just for a second. I've got this number here, right? It's negatives. The final units we came out with was kilogram per meter second squared, correct?
Yeah.
This ends up then being a Newton is a kilogram meter per second squared. We agree?
Yeah.
Okay, so we end up with, let's just do this in small steps. That's equivalent to each other. So this number here, the negative 30,312.9, that's a Newton per meter squared.
Newtons per.
Okay, so now if you look at your chart, there should be a conversion. Is there a conversion?
Yeah.
Okay,
And then
so I have negative 30,312.9 Newton per meter squared. I believe it's 10 to the fifth. Is that correct?
Yep.
Okay, and we're gonna end up with a weird answer, but it's okay. Newton per meter squared is then 1 bar. So what do we end up with? We're gonna end up with a little tiny decimal point, but that's okay.
.303. Yes.
Okay, negative 0.303 bars. So doing the problem this way, 4.15 minus 0.303 is going to be pressure of the air. So that ends up being what when you subtract that?
3.85.
3 point what? 4.
85.
What is it?
I got 3.85.
Okay, nice and loud.
3.85.
Thank you. All right, 3.85. Now, this is not a logical answer, is it? Okay? If we were doing this with the correct density, just to let you know, if you did it with, and I will accept that because I screwed up. That's true on exams. When I screw up on exams, if I screw up like that, I'll accept it with whatever numbers are in there. All right, because it's my problem, it's not your problem. Kilograms per meter cubed. Actually, the problem was the PDF file. That's another issue. Okay, so 10 to the third kilograms per meter cubed. Okay, so if you do that, you end up with an air pressure of 1.21 bar, which is much more reasonable because atmosphere is at 1 bar. All right, see how it works? Yes,
I kept mine at 10 to the third, so it's okay.
that's fine. Sure, I'll take it either way. Yes,
Scroll back up.
oh, yeah. And I put in the, you want me to scroll down? I put in the chat, the, I don't know what I put in the chat. I put in the chat, the, Dropbox. And it is open. All right. So we are going to move into work and energy, which means you are going to have a quiz on work and energy or section 2.1 on Wednesday. We are alternating. Okay, so since we did group work on 1.5 through 1.9 with pressure, then we will do a quiz on 2.1. Had anyone tried the homework for 1.5 through 1.9? Did that problem look familiar? Yeah. So if you do some of the 2.1 homework, guess what? That's the problems that you got the quiz problems in front of you. It's the 2.1 homework. All right, numbers might change, problems stay the same. So we're going to talk about energy and work. All right. I was interviewing a tutor this morning. I actually gave him a problem out of this section, out of chapter 2. It's 2.3, 2.4, something in there. And I managed to stump him. So he's got some reviewing to do before I'll recommend him for you guys. All right, so let's go ahead and spend some time with energy and work. We're going to start off talking about kinetic energy, but we're gonna think about it a little differently. Kinetic energy, what does kinetic energy mean to you?
Force times gravity times height.
It's what?
Force times gravity times height. Oh, no, sorry, 1/2 mass times velocity squared.
Okay, yeah, you were completely confusing me. All right, 1/2 mv squared, right? That's what we all learned back in calculus, correct?
Mhm.
All right, we're gonna look at kinetic energy in two ways. By the way, I want to break this down because we're gonna have three different types of energy. Kinetic energy is when we have mass moving. Right? If the mass is not moving, if I tell you we have a closed system, the kinetic energy has to be what? 0, because the mass is not moving. All right. When we solve for kinetic energy, typically we run the integral like this, where this goes from V1 to V2. All right. In this class, though, we already talked about when I have an open system, what's happening?
Mass is leaving.
Mass is moving. So in this class, you will also see kinetic energy with a dot over it means what?
The derivative with respect to time.
Derivative with respect to time is then going to be, we are going to run, for this class, we are going to assume volumes are constant. There's a 1/2, I'm losing, I lost a 1/2. Okay, so the mass is changing with respect to time. Excuse me?
There's supposed to be a 1/2 in the other one or no?
No, because when you integrate it, the 1/2 will appear.
But it is supposed to be squared, right?
Not until you integrate it. So what happens if I integrate this, right? What are we gonna have? mv squared, because I'm integrating with respect to v over 2, evaluated from v1 to v2.
I meant the one with dots on it.
Oh, yeah, this one needs a v squared. All right. Okay, so once again, if we have a closed system, and that's why that was on your last quiz, your kinetic energy can automatically, then you can write it down that it's going to be 0. All right. It's an open system, not necessarily the case. If we're pumping stuff, not necessarily the case, right? Because then the water's moving, so the mass is moving with a particular velocity when we are pumping fluid. All right. Do we need to go over a physics kinetic energy? Sure. All right. So we throw a standard 5-ounce baseball, 80 miles per hour. What is the kinetic energy? So you hopefully did this problem back in physics 210. All right. We want this in kinetic energy. You're not given units, but let's say we want it in joules, which is going to give us a bit of a nightmare. All right. Because joules is SI units, isn't it? We're going to have to start off dealing with this. Now we know kinetic energy equals 1/2 mv squared, right? We also know a joule. I don't have a joule breakdown. Kilogram meters squared per second squared. Is that correct?
Yes.
Is that correct on your charts?
Yeah.
Okay,
Yeah.
yeah. So it's also known as a Newton meter. Okay. All right. So that being the case, this 5, is it in kilograms? No, so I can't plug it in directly, can I? I want it in kilograms, so we're gonna start off with 5 ounces. All right, and then we know in 1 ounce, I have 0.02. Is that what you see on your sheet? 0.02834 kilograms.
I don't see this.
You don't have ounces.
I don't see that. Let's see.
Okay, you don't have any mass conversions on your sheet?
We have mass, but I don't see ounces. Yeah.
Oh, okay.
And say 5/12 to turn into pounds.
5/16.
I'm sorry. Can you say 5/16 to just turn it right into pounds?
Okay, do you have kilogram to pounds? Okay, so let's do it that way. All right. So we know there are 16 ounces in 1 pound. Right, and then what's the conversion between pounds and kilograms?
1 kilogram to 2.2046 pounds.
To what?
2.2046.
All right, so we, hopefully you guys are putting this in a calculator, or you already, and you came up with 0.022. Or no, 0.14 kilograms. Did you get that?
Say that again, sir.
0.14? Okay, so my answer is 0.14 kilograms. I have some folks training in the back, so let me roll this up for them. All right, so my mass is now in kilograms, right? Look at where we need to be. I have another problem. I have 80 miles per hour. Is that gonna work for me?
Nope.
No. Why not? Because I want it in joules. So I need it in meters per second. So this one I know is right. So in 1 hour, I have 3,600 seconds. Workspace 1 has accessed my device. All right. No, you know what it is? It's Pima's way of looking for updates.
That's what they want you to think.
Huh?
That's what they want.
No, they're really spying on us. Miles per second. In fact, I gave Big Brother a bad idea the other day. I did, because they're like, we don't know how we can track. Faculty are supposed to be on campus 29 hours a week. No worries, I'd do that with time to spare. But they said, how could we possibly track it? I was in a leadership meeting and I'm like, you people, we all have to badge into everywhere. You're like, oh. They're gonna make us badge into classrooms, except this classroom doesn't have a thingy on it. I now need to go from miles to meters, correct?
Yeah.
Is this on your conversion sheet? Or do you have to go to feet?
To go to feet.
Okay, so in 1 mile, how many feet? It's 5280?
Yeah.
All right, and then what is the conversion between feet and meters? It's 3 something.
3.3048.
Nice and loud.
0.3048 meters per foot.
All right, so you come up then with 35.7 meters per second.
I got 35.8, yeah, or. Yeah, 35.7632, yeah.
Okay. So now I can put this into my kinetic energy equation because I have fixed my units. Fix your units on the front end. It'll make your life easier. So let's see, we have 0.14 kilograms And then we have 35.76 meters per second squared. So the kinetic energy of my baseball. What did I do with it? Oh, there it is. 89.7 joules.
Yeah, 9.5.
Oh, you got 89.5?
Yeah, I rounded differently, I think.
Okay. All right. Okay, change units early. Where am I going? All right, someone else told me this. What is potential energy? Who told me what this was? Was that you, Ben?
Maybe.
Maybe?
It's right, yeah.
Okay. Ben said it's mg. Now, he said h. Okay? Your author doesn't use h. Your author uses mgz. Typically because h means other things. All right? So this is what? This is your pumping uphill problems. We aren't going to do any electromagnetic. Have you guys hit that yet in 260?
Not.
No? Where you calculate potential energy based on magnetic field?
Circuits.
You're doing circuits. I don't know if you actually ever hit that.
I don't think
Do you do in 216?
Yeah,
It sounds
Yeah.
like it.
260 we did.
Okay.
I don't
All right.
like that concept.
Once again,
Yeah.
if we're seeing how the potential energy changes with time, we are going to be looking at how the mass is flowing and how tall it's flowing. The only place you're going to see potential energy is when we are pumping stuff uphill. So I'm telling you right now, that's the only time. Should we do a calculation for potential energy? No? Okay. All right.
Minky?
Yeah.
So in this is the change in potential energy over time.
Mhm.
So in the other one, where was the kinetic energy, should we have it had a dot over the M or the B?
And
It should be over the M.
Over the M? Okay, maybe I missed that.
It was just light.
Oh, okay.
Yeah, it was like
Okay.
the tiniest thing.
All right. Okay. So here is one of your homework problems. A vehicle crumple zones are designed to absorb energy. Okay, so those are your bumpers during an impact by deforming to reduce transfer of energy to occupants. All right, and so currently cars are designed so that if you're in an accident, the engine will actually fall out. Has anyone seen that happen yet? Your engine arms will, if you ever, okay, so have you ever seen an accident where the engine's on the ground and the entire front end is all crumpled together? Okay, it is all purposely designed that way because in the good old days, the engine would end up in your lap and kill people. So now the engine falls down and you break those rocker arms, your engine mounts break, it falls down, and then the rest of it can take and absorb the energy by crumpling. How much kinetic energy must a crumple zone absorb to fully protect occupants in a 3,000-pound vehicle that suddenly decelerates from 10 miles an hour to 0 miles an hour? All right, and it doesn't tell us this, but we are going to calculate this in terms of it does tell us we want it in BTU. BTU stands for what?
British thermal unit, I think.
British thermal unit. Okay, and it's the energy that gets produced when you what is it? To boil 1 ounce of water and raise it 1 degree. That is what a BTU is. All right. What's happening here to the kinetic energy? We're going to have a change in kinetic energy, correct? All right, and so if you think about it, we have our final kinetic energy minus our initial kinetic energy. That's then going to ultimately equal the change in kinetic energy. All right, so if we want this in BTU, let's back up. If we want it in BTU, we're going to have it in, we're going to have to convert it to, we got it in pounds. That miles per hour is going to give me a problem, isn't it? The other problem is to convert to BTU, do we use pounds? Look at your sheet. We have force pounds per, or force pounds foot. Okay, it's not over anything. Force pounds foot. So we're going to have to convert our pounds into force pounds, aren't we? All right, so let's go ahead and start with that. The other issue we're going to have is we are given this in miles per hour. The zero we don't care about. Oh, there was an equal sign and a minus sign there. All right, so let's go ahead and do that to start with. If I have 3,000 pounds, how do I convert that into force pounds? That's 300. 3,000 pounds, how do I convert it into force pounds? Oh, wait, we're going to have to get it. Hang on, we can't do, well, it's going to be gravity to convert it over. But then we're going to have, oh, that's okay. Let's just go ahead and do it. All right, so it's going to be 32.174. This is force pounds. This is pounds, feet per second squared. All right, so do that calculation for me. Alicia's got my back. Everyone else is checked out. I have 32 more minutes of your life. Don't check out yet.
93.
Something trivial I'm missing, but isn't force pounds or pounds force and then 3,000 pounds mass?
Okay, so force pounds includes gravity. Pounds in this class does not include gravity. So that's why we're dividing by 32.174.
So it's just already implied by 3,000 pounds. That's pounds.
That's just pounds. It's given 3,000 pound. Okay, but it's not in force pounds. I know, but we need to move it to force pounds to get it to BTU. So what answer did you come up? It's gonna be like 9 something.
93.24.
93.24. Let's watch this. This is going to end up being LBF seconds squared per feet. All right, so that is our new quote unquote. Here is our M value. We now need to figure out our velocity value. 0 is always 0, but we got to deal with the 10 miles per hour. So what am I going to have to, how am I going to turn this into, and this is miles, right? Correct? Not M is in meters. All right, so we have what? I guess we'll deal with that first. We have 5 in 1 mile. We have 5280 feet. All right, so that means we are going to have 52,800 feet per hour. Correct? What's up? Did I make a mistake? I lose a zero, add a zero?
I don't think so. I was just wondering, the mass equation in the middle,
Yeah.
why did you use LBF and then LVFT?
Okay, so LBF means gravity's included,
Oh, you just said that.
okay? So LB means gravity is not included for this class only. In statics, LB means gravity's included, doesn't it? All right, in fluids, LB will not be including gravity because we already learned about what? We learned that force, when it comes to gravity, changes. All right, in fluids, you will not have LB, you will have slugs. LB is now includes gravity, weight without gravity in British units or imperial units is going to be slugs. So I know it's very confusing. So you just put a sticker on your door, on your bathroom mirror. So when you brush your teeth, right? LBF is not LB for this class. Okay. Those of you that are all, how many of you are also taking statics right now? So there you leave LB alone. This class, you got to get a little more sophisticated with it. Demetrius is taking fluids. In fluids, we deal with slugs. All right, so I now need to deal with this. This is in feet per hour. Do I want it in feet per hour? No. So let's see, we have 3,600 seconds in 1 hour. So what number do you come up with when you do that? Thomas is running numbers back there.
I got 14.67 feet per second.
Julian is having internet problems. 14.76.
6.
Is it 6.7? Y'all be very loud.
6.7.
Feet per second.
14.6 per meeting.
Oh, rounded up, it's basically 7, so 6, 7, about. Okay.
All right, so now can I plug this into my equation? Kinetic energy final minus kinetic energy initial. The answer is yes. So we're going to have 1/2. M is now going to be 93.24. LBF second squared per meter. We are then going to have 14.6 meters per second squared.
Didn't we get
I don't think
Per
we
foot?
finished converting to meters.
Yeah, we only got 2 per foot, on the 93.2.
Wait a minute.
No, we want to stay feet.
No, we want to stay in feet. You guys are right. Okay, hang on, let me back up. This is in feet, right?
Yeah, 14.67.
4.67 is feet per second, correct?
Oh, I just.
All right, am I okay now? Okay, yeah, that's in feet per second. That has to be in seconds squared per feet. All right, and then this is going to be -0, right? Because we decelerate to 0. All right, so multiply this together for me.
$10,074.
And our units then are going to end up with feet, force pounds. So we know from the conversion chart, we can go to BTU 778, right?
8.7.
Okay, so 778.17 feet, force pounds is then going to be 1 BTU. And our final answer is what? 12.89 BTU. Something like that?
Yes.
I'm sorry, Luke, I don't understand 6/7. All right. Let's talk about it for a moment. That's how much kinetic energy is being absorbed, isn't it? What's this for? What's going on? Somebody talk to me.
It's just internet meme. When you did, they said 6-7, you just do it.
Oh,
I'm sorry.
What is that?
it's an internet meme. I don't get it because I'm a little old lady. Yeah.
Could you like really quickly go over why the mass is pounds force times second squared all over?
Sure. Okay. So if I have mass in pounds in this class, that is not a force. Okay? To find the force is going to be M times G, isn't it? So to find the force, we would then take, this is going to be pounds, and then we have that 32, or G is going to be whatever the gravity is. We'll say it's 32.2. Sorry. Feet per second squared. All right. Okay. So that would then give me my LBF, wouldn't it? Okay, so, but we had to do, what happened is we wanted to get into LBF and we had pounds. So we ended up then, the conversion, so if I have 10 pounds and I want to convert it to LBF, right, it's 32.174 is my conversion. So that's LB feet per second squared. So our mass ended up being what? If we have LB and then I have a second squared divided by feet, right? Which is what we ended up with. We know LB is LB feet, LBF per second squared per feet. Now I'm back to just pounds in LB. So it's just a different way to express the mass. All right, so we need to talk about work. Before we do that, I'm going to jump ahead a little bit and we're going to talk about the energy balance equation. Because this is what
Could
we're
you
going
go
to
back
use.
really?
You want to go back to the problem or to the LBF explanation?
Just the LBF explanation, like just super quick.
We know when we're good. We okay? We see you're talking, but we don't hear you.
Okay, that's good.
Okay, the other thing is these all get posted. So energy balance equation. This is the meat and potatoes of this class. We're going to spend the rest of the class working with this equation. All right, and this is the energy balance equation. It's the change in kinetic energy. We will work with it in two different forms. Change of potential energy plus change in internal energy equals Q minus W. When we have a mass flow rate, things are going to change around a little bit. Okay, we have talked about two of these, haven't we? So change in kinetic energy, we know. Okay, kinetic energy of final minus the kinetic energy of the initial. Change in potential energy. Same thing. Potential energy final minus potential energy initial. Now, if mass is not flowing because it's a closed system, both of those are going to be what? Zero. So if you see the words in the problem that say closed system, you can automatically write down kinetic energy is zero. Change in potential energy equals zero. All right. Now, delta U. This is the change in internal energy. If we were chemical engineers, we would spend the rest of the class on this. Okay? Logan says no.
Who was?
Yeah, he said, no, cut that. We're not doing that. Okay? What we're going to do is literally, we're just going to look this up. All right? That's why we're using those steam charts. It is a chemical reaction is what's happening. If I go from water to steam inside a sealed container, right, there is a change in that internal energy, isn't it? For the water to become steam, it has to change its internal energy. Julian must be having internet problems. Okay. We then have Q. Q is heat. Right? A lot of times we're either solving for Q or Q is given to us. We then have W. W is going to be work. All right, and we need to understand how to calculate work. I failed them in the spring. They struggled with calculating work the entire time. So we're going to spend some time talking about how to calculate work. All right. Because we're going to do it a little bit differently than you folks have done it in your previous lives, so to speak. Right? Let's go ahead. How did you define work back in physics? What's that?
Clarify, all the energy added up is work on C or E. I thought you had Q minus. W minus Q.
That's what I have.
I believe it's Q minus work.
Thank you.
And now you're questioning my sanity. I have to figure it out. Oh, this is all on calculating work. All right, I'm almost sure. All right, explanation of work. How did you do work back in your physics class? What was work?
Times distance.
Force times distance. You also calculated using, you could use an integral, couldn't you? Right? When we are dealing with gases, we are dealing with what? What did we calculate on our group work that we did?
Pressure.
Pressure. pressure is force divided by area, isn't it?
Yep.
Okay. So our work for this class is then going to be our pressure dV. You can think of it this way. If we have a pressure, if we have a pressure volume diagram, right? And let's say I have a constant pressure, but I want to go from 4 liters to 10 liters. That's going to take some work, isn't it? When we draw these pressure volume diagrams, we usually put arrows to say which way they're going. Even if I went from 10 liters to 4 liters, that's going to take some work, correct? If it's a piston moving, that piston, I'm going to have to put some work into the piston to get that to happen. So our work is basically the area under this curve. To find area under a curve, that's going to be dV. All right. Now, this situation, yeah.
What are the 2 axes here?
Pressure is one axis and volume is the other one. Yeah. All right. So this has a constant temperature involved. Here comes yucky vocab. This is assuming a constant temperature. We're going to call that an isothermal. So if you're doing a problem and it says you have an isothermal environment, well, then Q can be 0 because the temperature doesn't change. But you can then use this integral to find your work. All right. If it is a fixed volume, right? Let's say we have a fixed volume. So now my pressure is going to change, but my volume is going to be fixed. We'll say it's 4 liters. So this once again is pressure versus volume. If it's a fixed volume and the pressure's changing, can I integrate under a straight vertical line? No. So then we say the work is going to equal 0. All right. By the way, this is called isovolumetric. Your author doesn't like to use that word a lot. He has a tendency just to say that the volume is constant or the volume doesn't change. It's also called isochoric. I don't know. Choric. All right. Now, this is where I don't teach it like the author teaches it. The author assumes you cannot integrate. Okay? I know you're much smarter than that. You can integrate. So you will be expected to integrate. Okay? All right. By the way, when you finish calculating this, if W is greater than 0, this is work done by the system. All right, so my car cylinder, I put some gas fumes in there. I light it on fire, it explodes, correct? Change in what? Internal energy.
That's for the isothermal one, right? Like that.
Oh, it's 0, yeah. Yeah, all right. So what happens is it creates movement, doesn't it? It makes work. It moves the piston. So now you're converting internal energy, which is that explosion, into basically kinetic energy, because it's causing the car to move. All right, and you guys are all mechanical-ish or aerospace. If it's less than 0, this is work done to the system. All right, let's do a problem. How are we doing on time? We got time to do April. Let's do this one. Oh wait, does this ask about power? That's about network, okay. This is a very standard problem. Take a picture, do a screenshot. Let's sketch out what's happening. So we have 3 processes here. You guys take pictures with your camera, and leave a blank to write it down. I will post these notes online, but I want to get into the problem. All right, so what's happening is we have 3 processes and we have information about each of the processes, correct? So we are starting with a pressure of 10 bars and a volume of 1 meter cubed. That is the first on our PV diagram, and notice what it says. Sketch the process on, oh gosh. Maybe we won't get through this problem. All right, Control Z, Control Z. All right, sketch the process on the PV coordinates and evaluate the work for each process. So let's go ahead and do that. We are going to then have P versus V. I am starting up here at 10 bar and here at 1 meter cubed. So I have a point here. All right, so what happens? Expansion from state 1, expansion means more volume, to state 2, where V2 is 4 meters cubed. So 1, 2, 3, 4. I don't know the pressure, but I'm given an equation for this, aren't I? Right? It's PV equals some constant raised to the 1/2. I'm going from state 1 to state 2. So I'm going to draw an arrow to show which direction we are going. Okay? It's curved because it's this equation. PV to the 1.5 equals a constant. All right? Next, we have a constant volume heating to state 3. So from state 2, state 3 is back up here at 10 bar. Constant volume, that means I'm going to have a vertical line because I've got volume on that x-axis, don't I? It's going to look like this. Okay? Finally, it says we have constant pressure to state 1. So it's going to look like that. We go back to state 1. Do you see how I drew the graph? It's quote unquote a sketch. This has a funny equation and we're going to have to work with that. And that is PV to the 1.5 equals a constant. Once again, I'm going to do this differently than the book. The book is going to get weird because he assumes you can't integrate. All right. Okay, so it says net work. We are gonna have our work net. We're gonna have three parts to it. We're gonna have the work from 1 to 2, plus the work from 2 to 3, plus the work from 3 to 1. Okay, that's my net work. Each part of this is going to contribute to the total work of the system. Are we making sense? Easton, does it make sense? All right. One of these I'm all excited about. Which one?
Work 2 to 3.
Work 2 to 3. Why does that make me excited? It's 0. This is going to be 0. I can write it as 0 because I've taken calculus and I understand that is a straight line. Now, this is where we are going to diverge from the author. Okay? The author at this point is going to give you all these bizarre equations for different processes, and you don't need them because you can do calculus. All right? So if we take the easy one, we only have 4 minutes left. Let's do which one are you most interested in? 1 to 2 or 3 to 1?
1 to 2.
The hard one.
The hard one. Okay. So I know PV to the 1.5 equals a constant. I have one. Oh, I'm okay. I have a point. I know when P is 10 and the volume is 1 raised to the 1.5, that's going to be a constant. So my constant has to equal 10. And that's going to have units of bar meter cubed to the 1/5. All right. It's okay. I'm not going to care about that because it's all going to cancel out for me. Now, so that means I can rewrite this equation. P then equals 10 divided by V to the 1.5. That was basic algebra. Can we now integrate it? Sure. So to find the work, that's going to be the integral of P dV. All right, so that is then going to have to be the integral of 10 over V to the 1.5 dV. We have a second problem. We doing okay? Ben, how are we doing? All right, we have a second issue. I know I start with a volume of 1. Do I know where I end? Can I figure it out? Yes, I certainly can, because I know that, well, actually, I don't need to do that because I know we're going to end with a volume of 4.
Yeah.
Okay, we were given that information. V1 was 1, V2 is 4. So this is going to go to 4. Now, this point, Lorenzo gets all excited because I'm not paid enough to teach you how to integrate. Okay? You can put it in your calculator at this point. You can put it in Desmos at this point. All right. The worst part is setting it up, and I believe you come up with an answer about 1.25 bar. Right? Oh no, that doesn't make sense that it would be in bar. What is the work?
Should be.
Yeah, so work 1 to 2, you end up with 1,000 kilojoules. You have to do some conversion to make that happen. We will pick up and we will look at what the answer is coming out of our calculators on this and how we get to the 1,000 kilojoules. We will start that then on, I don't know what day of the week, Wednesday. Can you take a quiz on kinetic and potential energy?
Probably, maybe.
Yes. Okay, I won't put work on your quiz. All right. So you're gonna wanna do the first part of the homework until it gets into these problems.
Okay.
All right, we'll do group work on these problems. Also have to move into 2.2.
She's saying we're gonna.
I need to take attendance. Don't go anywhere. If you're here, please let me know. Because I need to take attendance. Dashboard.
So we will have to, you show me.
All right.
So we technically know that.
Okay, Diego.
Here, what about the?
Logan.
Here.
Riley.
I'm online.
Excellent. Hector.
We just.
Online.
Oh, Hector's online. Okay. Daniel.
Here.
Gael.
Here, I'm here.
Christian. Chelsea. Ben.
Here.
Valerie. Thomas.
Here.
Demetrius.
Here.
Anthony.
Here.
Alicia. And Easton. If I called your name, you may leave. If I didn't call your name, hang on for 30 seconds. I gotta get to the other course list. That's my 0 contract. All right, Mohammed.
I did one of them, no one noticed.
Well, you did one? You did one? Oh,
Yeah, look
shit,
there,
I missed
look at
it.
it.
I missed you.
Atreyu.
Here.
Julian. Julian was here. He's
Here.
going out. Me.
Here. He gave us the shave.
Sam. Gabriel.
Here.
It's like a
Chase.
I can't
Here.
stop.
Martine.
Here.
I'll take it.
All right. Emmanuel.
Here.
Look.
Here.
Michael Vega.
Here.
And Lorenzio.
Here. You have to get the gym right now.
All right, you guys are dismissed. I will see you on Wednesday. Do some
Dr.
homework.
Ricky, I think you called my name for attendance twice. I'm not sure. Is that okay? Am I marked down for today?
Who are you?
Gael.
Yeah, you're marked down for today.
All right, thank you.
Quizzes. Free class.
I don't have any, I don't have any done up.